Now we'll talk about the example of a bomb being dropped by an airplane. And over here on the left side, you see the bomb fastened underneath the belly of the airplane, and it's released and it falls downward. What you see in this picture is the airplane shown at 4 different moments in time, and these moments in time are equally spaced. The plane's moving at a constant speed, so the distance it moves in each increment of time is the same. The bomb, though, accelerates down, so the vertical distance that it has fallen after each increment of time gets larger and larger. It gains more and more downward speed. As always, the key to understanding this or solving a problem of this nature is to treat the horizontal and the vertical motion independently. Now, when the plane is flying and carrying a bomb, at the moment the bomb is released, the bomb has the same velocity as the aircraft. In other words, its initial velocity is not zero, and you see this initial velocity vector drawn in the diagram. The initial velocity is the initial velocity of the plane. In this case, the bomber is flying horizontally. That means the bomb has an initial horizontal velocity. And in this case, it doesn't have any initial vertical velocity. Once it's released, though, it begins to accelerate down due to gravity, but it also continues the forward motion that it had when it was being carried by the plane. So this forward motion of the bomb has to be taken into account by the people doing the bombing, or they're going to miss their target. If they were to wait till the plane were right here over the target and then release the bomb from directly above the target, the forward motion of the plane, which gives the bomb forward motion, that would carry the bomb forward of the target, and it could miss the target by a substantial amount. So the bombardier has to take into account the forward motion of the plane and its height above the ground, and release the bomb a certain horizontal distance before it gets to the target, such that by the time it falls that distance to the ground, it has moved forward that distance and hits the target. And exactly how far in advance of the target the bomb needs to be released is a projectile motion problem. In this example, we're told that a bomber is flying at an altitude of 1 mile and a speed of 300 miles per hour. And this might be typical of a World War II bomber. There were different types of planes that flew at various speeds and all different sorts of altitudes for different bombing runs. But this might be typical for a World War II bomber on a bombing run. And we're asked to find how far ahead of the target must the bomb be released. So here's what we'll do. I'll start by converting things into our standard units, meters and seconds. 1 mile is 1,609 meters. And then the 300 miles per hour, I'll do a unit conversion. I know that there's 1,609 meters in 1 mile. So the miles will cancel out. And I know that 1 hour is 3,600 seconds. So the hours cancel out. And I'm left with meters per second. And when I do the math here, 300 times 1,609 divided by 3,600 is 134 meters per second. So that's the initial velocity. Now, to solve this, I treat the horizontal and vertical motion independently. So I'll do the vertical this case. Do the vertical first in this case. I know the vertical distance. It's 1 mile, or this many meters, 1,609 meters. So I can find the time it takes the bomb to fall. The time that it falls depends only on the height. The horizontal speed doesn't affect the time it takes to fall. So vertically, this is what I know. V0, the initial velocity, vertically is 0. The plane's flying horizontally. The acceleration will be 9.8 meters per second squared. This is assuming that down is the positive direction. And then I can say the initial position is 0 and the final position is 1,609 meters. And it might help you to make a little sketch to visualize that. You can Draw the bomb here. It's moving along at its initial velocity, and it's moving down like this. If we can consider down to be positive, then the height right here is 0 meters, and here it's 1,609 meters. And you should see that the 0 and the 1609 set up like that is consistent with down being the positive direction. So here's what we'll do now. Y is y0 plus v0t plus 1/2 at squared. And because it was launched horizontally, the initial velocity was 0, so that ends up being 0. And the way we've set this problem up here, the initial position is 0 also. So we just have this equation, y is 1/2 at squared. And we can solve this for t. T ends up, when we do the math, ends up being the square root of 2y over a. And that's the square root of 2 times 1,609 meters divided by the acceleration of 9.8 meters per second squared. And I put all those numbers into my calculator, multiply, divide, take the square root, and I get a time of 18 seconds. So that's how long it takes the bomb to fall. That means we need to release the bomb 18 seconds before the plane is directly over the target. And that will determine the horizontal distance before the target. So I figure out that distance using the horizontal motion. So horizontally, this is what I know. The acceleration is 0 horizontally, and the initial velocity we calculated was 134 meters per second, and now I also know the time is 18 seconds. And you can just say this, x is vt. Remember that equation just came from this, x is x0 plus v0t plus 1/2 at squared, where the acceleration is 0 and the initial position is 0. So we just have distance is velocity times time. And if you recognize that, you don't have to write out that step. You can just go straight to this, x equals vt. And that's 134 meters per second times a time of 18 seconds. That gives us 2,400 meters. So the bomb has to be released when the plane is still 2,400 meters away from the point directly over the target. And that's a substantial distance. That's about 1.5 miles. If you didn't take that into account, you would miss your target by 1.5 miles. In the real world, bombers have to account not only for the motion of the plane, but also for air resistance. And air resistance really does matter at speeds like this. So in the real world, the problem is actually more complicated. But this does illustrate an important point, an important concept of projectile motion.
Hi, this is a physics projectile motion problem. It says that a player kicks a football with an initial velocity of 15 meters per second at an angle of 42 degrees. So if we draw that here, let's say the ball is thrown from here and it lands over there. So the initial velocity is 15 meters per second, and it's 42 degrees, and a guy throws it from here, and another guy tries to catch it. Okay, and the question continues. As the second player is standing at a distance of 30 meters from the first in the direction of the kick and starts running to meet the ball at the instant it's kicked, how fast must he run in order to catch the ball before it hits the ground? So they're asking, so this guy needs to run here before this ball touches the floor here. So they're asking how fast should he run to catch the ball. So in order to know that, you need to find how long the ball is in the air and what distance he has to run, right? So v equals displacement over time. So we'll use two equations to find time and then displacement. And time is always calculated by the vertical velocity. Displacement is always calculated by the horizontal velocity. You just have to remember this. Okay, and dividing a vector into its vertical and horizontal components, there is an easier way to do this. So that's the vertical, different color, vertical and horizontal, right? Okay, write 15 because both of them have 15. It's either cos 15 cos 42 or sine 42, 15 cos 42 or sine 42, but those two are different because they're obviously different vectors. So how do you know if it's cos or sine? There's an easier way to do this. If the angle can be here or here, right? So if the angle is closer to what you're finding, first we're finding this. If it's closer, C for cos, C for closer, then it's cos 42. If it's far, because it's 42 is not right here, it's right here, and it's not touching this line, right? So that'll be sine 42. Great. Now you found the vertical velocity. You need to find the time. First we'll find the time till here, and then times it by 2 to get the total time right here. So what equation do you think we can use? We have the acceleration, velocity, and we need to find the time. So we find basic equation: acceleration equals final velocity minus initial velocity over delta t. Since we're finding delta t, we can switch these around. So it'll be delta t equals, same thing, v2 minus v1 over a, acceleration. Okay, this is v2 and this is v1. We know it's v1, we just figured that out. 15 sine 42, that's 10.04. So that's 10.04. And what's this? So as the ball is rising up, the gravity is slowing it down, and then right here it's 0, and then when ball is falling down again, it's speeding up because the gravity is pulling it down. So v2 equals 0, and v1 we just found out it was 10.04, and acceleration, it's not 9.81 but it's negative 9.81 because this thing is traveling up and gravity is pulling it down, so it matters, vector, so direction matters. So when you divide this, you get a 1.02. Okay, sorry for the interruption. So t here we found to be 1.02 seconds. So you double this, you get 2.04 seconds in total at time. So right here you found out what's t, which is 2.04, right? And I forgot to do this. They actually tell us that these two players are 30 meters apart, right? You don't know where the ball will land and where he'll go to catch it, so that's an x. And this is obviously 30 minus x. This is all in meters, right? Now you need to find the distance that he needs to travel, which is x right here. X is also appearing here, so if we find this, we can find x. And how can we find this? As I said earlier, to find the distance, you just use this formula, which is very famous in most of the projectile motion problems. Delta D equals V1 delta T plus half a T square. Yeah, you just have to memorize this. So distance, as we're finding this distance, and it's 30 minus x equals V1, which is right here. That you type it in the calculator, you get 11.1. You just found the time, 2.04. And you really don't need to do this part right here, because acceleration is 0. Horizontal acceleration is 0. So it'll be plus a big 0. Right here, so if you type the whole thing in the calculator, you get x equals 7.3. So distance here is 7.3 meters. When you type that into the calculator, you get 3.6 meters per second. So he needs to travel 3.6 meters in 1 second, and only then he can catch the ball. So by looking at this, you know that you have to be a fast runner to play a football. That's interesting.
Projectile motion. Observe the athlete throwing a javelin. The javelin follows a curved path and lands on the surface of the earth. Such objects like javelin, which moves along a path determined by gravity and air resistance, are called projectiles. The path followed by a projectile is called trajectory. An object dropped from a height, an object thrown vertically upwards, and objects thrown obliquely upwards are examples of projectiles. In all these cases, the influence of air resistance is neglected. The velocity of the projectile varies from point to point. At each point, the velocity has components in the horizontal and vertical directions. The horizontal component of velocity remains unchanged throughout the flight. The vertical component of velocity continuously changes due to the force of gravity. Thus, the horizontal motion is a uniform motion, and the vertical motion is a uniformly accelerated motion. The magnitude of the vertical component is different at different points and is directed vertically downwards. Let us now analyze the motion of a projectile thrown obliquely. Let a body be projected from a point O with initial velocity VO. The projectile makes an angle theta with the horizontal axis. The velocity of the projectile at any point of the trajectory goes on changing both in magnitude and in direction. The velocity can be resolved into two rectangular components, V0 cos theta along x-axis and V0 sin theta along y-axis. There is no acceleration in the horizontal direction. The vertical component of acceleration AY is equal to minus g. Substituting the value of AX and AY in equations 1 and 2 respectively, we get, that is, the vertical component of velocity changes with time, and at the highest point, the Vy becomes 0. Let us now find out the resultant velocity of the projectile at any instant. The resultant velocity v is equal to vector vx plus vector vy. By parallelogram law of vectors, v is equal to square root of vx squared plus vy squared. V is equal to square root of v0 cos theta whole squared plus v0 sin theta minus gt whole squared. The direction of the projectile at any instant is given by the angle between the velocity vector and the horizontal. Tan theta is equal to vy divided by vx. From the equation vy is equal to v0 sin theta minus gt, it is clear that vy decreases when t increases and becomes 0 at p. At this point, the velocity is only along the horizontal direction. With further increase in time, the vertical component of velocity gradually increases in the downward direction till the particle strikes the ground. Horizontal range. The distance from the point of projection to the point where the projectile strikes the horizontal plane is called the horizontal range. It is denoted by the letter R. Time of flight. Time of flight of a projectile is the time taken by it from the instant when it is projected to the time when it strikes the point in a horizontal plane passing through the point of projection. T is equal to 2v0 sin theta by g. Range of projectile. Range of projectile is defined as the distance between the point of projection and the point where the trajectory cuts any plane. R is equal to v0 square sin 2 theta by g. Maximum height. Maximum height is the maximum value of the vertical distance attained by a projectile above the horizontal plane to the point of projection. In the figure, P is the point of maximum height. H is equal to v0 square sin square theta by 2g.
Next, I'll discuss the main concepts behind projectile motion, and I'll use this example scenario to demonstrate the main ideas. This is the case of a car driving off of a cliff, and my students always like me to draw the guy driving the car. His name is Speedy, and he looks like this. He has to drive a convertible because he has this huge head, as you can see in the picture there. Now, Speedy's a cartoon character. He can do this without getting hurt, but you can't, so obviously you shouldn't be driving a car off of a cliff anywhere. But here he goes, flying off of this cliff, and he starts off moving to the right. In this example, he starts off, his velocity, his initial velocity is horizontal, so he's leaving the cliff, moving completely to the right, not up or down at all. But gravity pulls him down, and so he ends up heading down to the water in a path that looks something like that. Now, here are the main ideas. The velocity at any moment is tangent to the path. So if I say this is v0, maybe 1 second later I could call his velocity v1. It might look something like that. Or after 2 seconds we might have v2 that would look something like this, v2, and after 3 seconds, v3 might look like this, v3. At any given moment, the velocity vector is tangent to the path. So the direction of the velocity changes as the path curves downward. The next thing I need to say is that the horizontal and vertical parts of the velocity have no effect on each other. And this is a general principle that applies to all two-dimensional motion. The horizontal and vertical motion can and should be considered independently. In other words, the fact that gravity pulls him down has no effect on his motion to the right, and the fact that he's moving to the right has no effect on the downward motion due to the pull of gravity. Next, I'll say this. Horizontal velocity is constant. If I draw in the components of these velocity vectors, v1 is to the right and down. So I could call this v1x and v1y, and v2 over here has components to the right. There's v2x and down, v2y, and then v3 here has a horizontal component, v3x, and a vertical component, v3y. If I've drawn this accurately, then the horizontal velocity is constant. That means v0 here is the same as v1x and v2x and v3x. All of those are the same. Gravity pulls him down, but gravity does not pull him forward or back. Gravity exerts no force to the left or to the right. So there's no acceleration in the horizontal direction. So the horizontal velocity doesn't change. The vertical velocity, though, is changing. And if this were drawn accurately, then there would be a steady increase in the length of these velocity vectors pointing down, the vertical components. Gravity pulls it down, so it accelerates down. There's an increase downward in the vertical component of the velocity. And then lastly, I'll say that mathematically, this path is a parabola. It's parabolic in shape. Now that's only true if there's no air resistance. In the real world, there is air resistance, which causes the shape to be a little bit different. But in the absence of air resistance, or at low speeds, when air resistance really is negligible, the path of the object is a parabola. Perhaps the most significant concept behind projectile motion is the fact that the horizontal and vertical components of the motion have no effect on each other. The horizontal motion and the vertical motion are completely independent, and they can and should be treated independently of each other. This fact leads to some surprising results in some situations. Let's consider this case. Suppose you're standing on the ground, and the ground is perfectly flat. And suppose you're standing here, and suppose you're holding a gun, and you fire a bullet out of the gun. So here comes the bullet. And you fire it perfectly horizontal. So there it goes, flying out of the gun. And suppose at the same time you hold another bullet out here at the same height, and you release it and let it fall straight down. So one bullet is falling straight down, accelerating down under the influence of gravity. The other bullet is flying over to the right. The one flying to the right, though, is also accelerating down under the influence of gravity. And it will go very far to the right. Bullets typically move very fast, hundreds of feet per second, or maybe even a couple of thousand feet per second. So it could go a long way to the right before it hits the ground. This diagram obviously wouldn't be to scale in this case. The point here is that the horizontal motion of the bullet, the fact that it's moving to the right, does not affect the vertical motion. It does not affect its downward fall. If we assume that the ground is perfectly flat, and assume there's no air resistance, so there's no aerodynamic effects on the bullet at all, these two bullets will hit the ground at the same time. This one may fall and hit the ground in a very short amount of time. That the amount of time it takes this bullet to fall this distance will be the same amount of time that it takes the other bullet to fall that distance. The fact that it's moving to the right doesn't change its downward acceleration. It doesn't change the pull of gravity or the time it takes to reach the ground. If they start at the same height, this one is fired from the same initial height that that one is dropped, they will strike the ground at the same time. They both start off with a vertical velocity of 0, and they both are pulled down equally by the force of gravity. Now, if you aimed this bullet up initially, then obviously it would go way up before coming back down, and it would stay in the air much longer than the one that was dropped. Or if you aimed your gun down a little bit, then this bullet would have a very high, very large downward component, and it would hit the ground almost immediately, and would hit the ground much sooner than the one that was dropped. But if they both start out with the same vertical velocity, in this case 0, they both end up hitting the ground at the same time. You can demonstrate this to yourself without a gun, just at lower speeds. If you have a table and a ball or some object, and you have someone stand over here beside the table, and this person holds an object right there, and then you stand over here, and you're going to give this object a shove, and it's going to go flying to the right, and when it gets to the edge of the table, it's going to start moving in a downward parabolic path like that. If right when it gets to the edge of the table, this other person releases this one and lets it fall straight down, then these two objects will be starting from the same position, and they'll both be starting with a vertical speed of 0. So one object leaves the table with a velocity to the right, and the other object is simply released at the same moment right beside it and allowed to fall straight down. And you'll see both of those hit the ground at the same time. And that will be the case regardless of the initial speed here. You could send this one flying really fast or just very slowly, but the horizontal speed won't affect the time that it takes to fall this vertical distance to the floor. And the one that is released with no horizontal velocity will fall at the same time. So they'll be moving downward. So you could see this like this. They both start at the same position, and then after this one has fallen a little bit, this one will be over here. And then when this one has fallen to this point, the one that was moving to the right would be about there. And they would both be at the same height above the ground at any given time, and they would both hit at the same time. And that's pretty easy just to demonstrate. Just have two people and a flat surface, and you can see that happen. The only tricky thing is that this person who's releasing the ball from rest needs to watch carefully and make sure he releases the ball right when the one moving horizontally gets to the edge of the table. If it's released a little bit early or a little bit late, they don't hit at the same time. But if the one dropped and allowed to fall straight down is released right when the moving ball gets to the edge of the table, you can see them hit the ground at the same time, regardless of the initial speed of the one moving horizontally.